Hello students, I am Raghunanda working as an assistant professor of physics. Students, in the last class you have studied in detail about the black body radiation. So in this class we are going to study the black body radiation spectrum, or we can say that spectral distribution of the black body radiation and the concept of energy density. So in the year 1892, two physicists by name Lummer and Prinsham, they conducted an experiment to study the spectral distribution of black body radiation. So the arrangement of the experiment is as shown in this figure. This is the source of radiation, or we can say black body radiation. So it is allowed to fall on a mirror, and the reflected light is allowed to fall on a fluorescent prism, and it will get dispersed, and again it falls on mirror M2 and is focused and fall on a bolometer. Bolometer records the intensity of radiation. So the deflection in the galvanometer gives the intensity of the radiation, and when the prism is turned to different directions, the intensity corresponding to different wavelength is recorded, and the graph of intensity versus wavelength is plotted, which will be in this fashion. Okay, so this would be the graph. This is the graph of intensity versus wavelength of black body radiation. Okay, now if you see this spectrum, so what you observe is at a given temperature, say for example 1000 Kelvin. So if the black body temperature is maintained at 1000 Kelvin at a given temperature, it is observed that the energy is not uniformly distributed, isn't it? So energy at different wavelengths is having different value. Now at a given temperature, the intensity of radiation increases with the increasing wavelength. At a particular wavelength, it will become maximum, and if the wavelength is further increased, the intensity of heat radiation decreases. So as we all know that black body is such an object which radiates the radiation of, or emits the radiations of all the wavelengths, but some of the radiations, they are minimum, or intensity of some of the radiations is observed to be minimum, and intensity of some other radiations will be maximum, and at a particular wavelength or specific wavelength, the intensity will become maximum, and that is known as the peak wavelength. Okay, next, the lambda m, that is the wavelength for which the intensity is maximum, decreases as the temperature increases, where lambda m is the wavelength for which the energy emitted is maximum. So you can see in this figure, so this curve for different higher temperatures, so you can see that the wavelength lambda m goes on, shifts towards the left side, isn't it? So it shows that when the temperature is increased, the lambda m value decreases. It shifts towards the left end of the plot. Okay, so that is why we can say that when lambda m increases, sorry, when temperature increases, lambda m value decreases. Hence, the product of the two will be constant. So, the energy emitted is maximum for a particular wavelength, isn't it? And it is observed that lambda m into T is equal to a constant. The point on the dotted line represents the lambda m at various temperature. This is known as Wien's displacement law. That is, the lambda m value will get displaced towards the left or towards the higher frequency side, isn't it? So that is how we can define Wien's displacement law. At the temperature, as the temperature increases, an energy emission increases for all wavelengths. You can see that as the temperature increases, so the energy, see for example, this is lambda. Assume that this is the value of lambda. For 1000 Kelvin, the point is here, but for the next curve for which the temperature is 1250, the value of the energy that is emitted is larger compared to the previous one, isn't it? So what this implies, as the temperature increases, an energy emission increases for all wavelengths. Next point is the area under the curve. The total area under the curve gives the total energy emitted by the body at a particular temperature for the range of wavelengths considered. So always the area under this curve gives the total energy emitted by the body at a particular temperature for the range of wavelengths considered. And as this area under the curve represents the total energy, and it is observed that when the temperature of the black body is increased, this area also increases. So the total energy emitted is directly proportional to the fourth power of the temperature of the body, that is E is proportional to T to the power 4, which is Stephen's law. So what are the characteristics of the black body radiation spectrum? So far we have studied. So at a given temperature, the energy is not uniformly distributed. How it is distributed then? At a given temperature, the intensity of heat radiation increases with the increasing wavelength, and after a particular or at a particular wavelength it becomes maximum, and then it starts decreases, and the wavelength for which the intensity is maximum is observed to be varies inversely with the absolute temperature, which is known as Wien's displacement law. As the temperature increases, an energy emission also increases. The area under the curve represents the total energy emitted by the body at a particular temperature for the range of wavelengths considered. As the temperature increases, it is observed that the area under the curve also increases, and hence we can write that the total energy emitted per unit area per unit time is directly proportional to the fourth power of the temperature of the body, which is nothing but the Stephen's law. So these are all some of the characteristics of black body radiation spectrum. Now let us know about another concept called as concept of energy density. So as we all know, energy density, how it is defined, it is the amount of energy stored in a given system or a region of space per unit volume. So energy density is the energy stored in a given system or region of space per unit volume. So in order to derive the expression for energy density, let us consider a hollow enclosure E, in which dV is the small elementary volume. Let us consider another imaginary sphere whose radius is small r and whose radius is very large compared to this unit or this small volume, and if length is the length of L, if L is the length of the cone through the volume, dV means from here to here. L is the length of the cone through volume, dV. dA is the elementary area on the imaginary sphere, and if A is the cross section of the cone, and then the solid angle of the cone is given by A by r square. If K is the specific intensity of radiation through unit solid angle per unit time, then the amount of radiation through the area dA is given by K into dA into A by r square. If time taken by this radiation to travel the elementary volume under consideration is L by C, where C is the velocity of radiation, then the total amount of radiation contained in the volume dV within the solid angle is given by K into dA into A by r square into L by C. Now, this A into L is equal to dV. Now, for the entire enclosure of radius r, it is given as summation of this. Now, after simplifying this, summation of K, this is summation of dV is V, C by r square. 4 pi r square is the surface area of the imaginary sphere. Now solving this or simplifying this, what we are going to get? 4 pi kV by C. Energy density of the radiation inside the enclosure is given by total radiation per unit volume. So this is the total radiation per unit volume, which gives the expression for energy density to be equal to U is equal to 4 pi K divided by C. So this is the very important expression you need to remember. Now, how this energy density is dependent on the temperature, let us see. The total energy radiated from an area in a region of space is given by Stephen's-Boltzmann's law. As we all know that this is equal to sigma into T to the power 4. So, in terms of energy density, how this total energy emitted per unit area per unit time is given means it is equal to C by 4 times the energy density. So it is very important equation, you need to remember this. So energy density in terms of emissive power, or we can say that the energy that is emitted per unit area per unit time is given as C by 4 times the energy density is equal to the rate of emitted radiations per unit area. Okay, now this energy density of radiation inside a constant temperature enclosure, it is quite independent of the nature or shape of the walls and depends only upon the temperature. So this is the dependency of the temperature, dependency of the energy density on the temperature. Although different bodies radiates at different rates, the quantity of the energy density of the radiation inside the enclosure remains unchanged as long as its temperature remains constant. So these are the points which depict the temperature dependence of energy density. Means the energy density of the black body radiation, it depends only on the temperature and not on the nature or shape of the body. So students, in this session what we have learned? We have learned about the spectral distribution of black body radiation, and we have studied the concept of energy density, and we have obtained the expression for energy density